Okay, hello everyone. Okay. I think today is week 12, right? So we'll do week 12. Are you comfortable with week 11 content? Am I audible? First of all,
Yes, sir.
yeah.
Yes.
So are you guys comfortable with week 11 content? Especially the one which is what like the transformations of random variable. I think we have seen that on Thursday. Are you guys fine with that? Okay, good. uh, any concerns regarding that content, because that topic again it will come today while we see that univariate and bivariate, sorry, bivariate and multivariate uh, random variable, right? And generally, uh, so in our syllabus of MLF we have univariate, sorry, bivariate and multivariate random variable, which is related to only normal random variable, right, or Gaussian random variable. So uh, both of them are the same distributions, right? uh, Again, I think we'll start right now with this part. Any issues if you have, right? Anyone, whatever the smallest doubt or anything it is there, right? That is fine. If you have any issues while understanding the transformations of random variable, you let me know. What I'm trying to do here,
Sir,
yeah,
previous week issues can we clarify at the end of the lecture?
uh, yeah, that's fine. Okay, we'll see
Oh,
that.
oh.
Is it's related to what, like
This new content only 10 11 week 10 11.
10, 11,
Yes,
or
sir.
okay, 10 might, okay, we'll see that how much time we'll get, because I'm not sure that whether we get much time today, but let's see. If we get time we can do it, or else we'll have to see them into the revision session only. But okay, I'll try to cover as much as possible. Week 10, week 11, whatever any issues are there, we can see that. Okay. Transfer, before that, okay, week 11, what was the concept we have seen? It was transformation of two random variable, right? Transformations of two uh, random variables. And what we have seen there is, you have, let's say, two random variables x and y, correct? And what is known for us, the joint density of these two random variables, it is known to me, which is f of x and y. Suppose there are two other random variables, uh, which is, let's say, x is a function of two other random variables, w and s, and y is also a function of two random variables. Let's say it's the function is called s, or sorry, w and s, w and z. These are the random variables. W and z are the random variables, and x is a function of these two random variables, and y is also a function of these two new random variables, w and z. In that case, how to find out the joint density between the or joint density of these two random variables, w and z? The formula for that is this one. So f of wz is equal to, in terms of, since I know this f of xy, this is known to me, right? It's known to me. In that case, f of wz, this joint density can be written as f of xy, right? And instead of x, what should I write here? I should write this r of w comma z, r of w comma z, and s of w comma z. And what else we have said, that it is uh, a modulus of determinant of a Jacobian, correct? And what is the Jacobian and what is the determinant of Jacobian? We have seen that it is, determinant of Jacobian is this one, del r by del w, del r by, or I'll say that, okay, del z. R means what? R is basically this r of w comma z, right? And del s by del w, del s by del z. right? That is there. Or I can write it like this, maybe del x with respect to del w, del x with respect to z, and these are the partial derivatives y with del z. Fine. And why we take the determinant? Because let's say you have written this in a so in the row wise, right? So I have taken the differentiation with respect to x first, and in the second row I have taken the differentiation with respect to the variable y. So suppose you have taken it uh, y first, the differentiation with respect to y first, and the differentiation with respect to x later. In that case, what will happen? So if I exchange the rows, what will happen to the determinant?
It will become negative.
The sign will change, right? So to accommodate that, we use the modulus here, right? In the formula. So this is the formula for finding out the joint density of W and Z, given I have known the joint density of X and Y. Correct? I hope this is clear. Again, I think we have discussed about continuous random variable previous session, uh, and one of the important continuous random variable is what? That is your normal distribution, right? So there is this distribution which is a normal distribution, or we call it as Gaussian distribution, right? Fine, so this is good. uh, Gaussian distribution, when we call for a normal distribution, when I said is that when your uh, z1, right? If z1 is a random variable, if it is normally distributed such that 0 and 1. What is 0 and 1 here? 0 is the mean and 1 is the variance. So if your random variable is 0 mean Gaussian distribution or 0 mean normal distribution, then we call it as, or we can actually, it is called as a normal distribution. Fine. Okay. One more concept we have discussed. I have not discussed it like explicitly, but while I think solving one problem, we have said that if the two variables, right? Let's say x and y are the two variables, right? And if they are independent of each other, so each of them will have the densities, right? F of x and f of y. If they are independent of each other, then what we say about their joint densities, right? So if they are independent, what we say about their joint density? It is equal to
Product of margin.
products of marginals, right? Fine. So this is what we have seen, and it is not only this rule is not only for two random variables. It can be used for multiple random variables as well. Fine. So let us try to see the what yeah, any question?
Sir,
Yeah.
so most of the time in the question it won't be mentioned, right, whether the random variables are independent or not. Like then how to identify it is independent or not.
No, no. If it is not mentioned, that means they are not independent, right? You,
But not always. No? If some if they
then
only
this is the way only. See, if it is not mentioned, then how will you find it out, like whether it is independent or not? There is no other way around, right? How do you do that? Correct. It has to be mentioned that x and y are independent of each other. If not, then I don't know like how to find out that, okay, whether they are independent of each other or not. Either they will satisfy this condition, that their marginals are equal to the joint density. Then in that case, I should know what is their joint density, and I should know their you know uh, uh, marginals, right? Otherwise, it has to be mentioned that whether they are independent of each other. Fine. Okay. So today, what we are going to see is that what is the density of or how does this density of bivariate and multivariate normal will look like. Again, we'll see that if we use a simple linear transforms on 2D normal, right? Then how does the densities will look like of this 2D normal or multivariate normal also, right? Uh, Fine. Let us try to see that. We'll see some of the or we'll see the derivation, and while seeing the derivation, right, we'll try to understand what where we have used what these concepts. Fine. Okay, so before going there, let us say you have the random variables like this. Z1 is normally distributed with uh, mean 0 and variance 1. Again, there is another variable Z2 which is normally distributed with mean 0 and 1. And like that, you have D uh, ZD, right? So, this variable D such variables you are having, and all of them are, let's say, zero min random variables, right? Okay. Suppose all of them are independent of each other, right? Then uh, what do you say about uh, their joint density? So what will be the joint density of them? F of z1, z2, let's say z1, z2, z3, to let's say zd of z1, comma z2, comma z3, that zd, right? So okay, what do you think about that? What is their joint
Product,
density? It will
product
be
of
product, right? So it is basically it is f of z1 of z1, then into f of z2 of z2, and such that it is f zd of zd, right? uh, but see, writing like this, it might be a cumbersome task to write all of this, right? So instead of that, what you do is you just create a vector z, right? And in that vector, what you do is you arrange all of these uh, normal variables, right? Like this: z1, z2, z3 up to zd. So it's a vector with what is the dimension of this vector? D cross 1, right? And now you write down their joint densities. What do you think their joint density? So when I write like this, f z of z, what does that mean? This means this z belongs to what? This vector, right? So I'm actually referring to this vector. So fz of z means the joint density of all of these random variables which are actually inside this vector. So what is a okay, what does how does this product will look like? So this product I can write like this, right? Product, pi is the sign for product here. Pi equal to 1, pi of I equal to 1 to d. So that means we are taking a product of all of these random variables from 1 to d, and let's say if it is f zi of zi, like this, right? Okay. But how does the each zi, right? what is what is the marginal, or what is the density of this each zi will look like? F zi equal to, what is it? 1 upon root 2 pi e to the power minus zi, right? Zi minus 0 whole square by 2 into 1 square, right? 1 square. So that means 1 is the standard deviation or variance here, or 1 is the standard deviation, or you can, yeah, now it's variance also, right? So I can say 1 square, or I can just write down 1, right? Because it's 1 square. So basically it will be 1 upon root 2 pi e to the power minus zi square by 2. Is that correct? Fine. That's okay. So when I wanted to write the joint density of this vector, then what does that will be? So it will be fz of z. When I refer to this z, that is a vector which is containing all of this z1, z2 up to zd, all d variables, right? So this is what multivariate normal will look like. And what is the density? The joint density of that looks like this: product of I equals to 1 to d 1 upon uh, root 2 pi, right? 1 upon root 2 pi into e to the power minus half zi square. Is that correct? Is that fine? Okay. And if I expand this product, so this 1 upon root 2 pi, how many times it will occur into that product?
D times.
D times, right? So what will be its product then? 1 upon, sorry. Yeah, so it will be 1 upon root 2 pi to the power d, right? And here what will happen to this?
Summation.
It will be summation. So it will be minus half summation of I equal to 1 to d zi square, right? That is the product. So that is going to be my joint density of this multivariate standard normals. So okay, this uh, the normal distribution or the Gaussian distribution with zero mean and one variance or one standard deviation, it is also called as a standard normal. So if I say standard normals, that means it will have a mean of 0 and a standard deviation of 1. Okay. If I further simplify this, how does it will look like? So this will look like 1 upon 2 pi to the power d by 2, right? So this root 2, it's like 2 pi to the power half, right? And if I multiply that half with d, then it will look like d by 2, and it will be 1 e to the power minus half summation of I equal to 1 to d zi square f z of z. So this is going to be my multivariate uh, density will look like, right? Multivariate normal density will look like if all of this z1 to zd, they are independent of each other. Okay, just remember that this also, like, to remember, let's say this is the second formula we have seen right now. This was the first one, and we will use these two formulas later on while seeing this derivation related to what? Related to uh, the simple linear transform of 2D normal. So we are going to see the simple linear transform of 2D normal. 2D normal means what? How does that vector will look like? The z vector. We have seen the multivariate case, right? So 2D is like z1 and z2, right? Only, so that's why like it is a 2 cross 1 vector, correct? So 2D normal, you can say it as a bivariate normal. Fine? Is that okay? Okay. Okay. So we will see some linear transformations, and we'll see the simple linear transformations. What do you mean by simple linear transformations? So the exponents will not be there, right? So any x1 square, or let's say if you have variables, random variables there, it will not be in the square terms, or the, like, it will not be in higher order terms. It will be only linear terms, like the order will be 1 for the random variable, right? Okay, suppose I define a random variable x1, which is equal to, which is a function of z1, fine, and that is equal to z1. and there is another random variable I define, which is, let's say, x2, which is row of z1 plus square root of 1 minus row square of z2. Fine. And row is here, it belongs to these two values, -1 to +1. Okay, so x1 is a function of random variable, function of z1, and x2 is a function of what? Z1 and Z2. Correct? Right? So are you able to see this kind of analogy here? The one which we have seen here. So there are two random variables x and y, correct? And each x is a function of w and z, and y is a function of w and z. Similarly, here you can see that x1 and x2 are the two different random variables, but x1 is a function of z1 and x2 is a function of z1 and z2. Fine. Okay. But if I wanted to write this transformation, right, is this a linear transformation? Yes, right?
Yes, sir.
Because z1 and z2, the orders, right, the exponents of them is 1, so they are in linear
Linear
transform,
combination also.
linear combinations basically. Yeah, right. So row and root of 1 minus row, these are the constants, right? So some constants, and
Scalar.
row is, yeah, and row are in between -1 and 1. Now this representation of these two random variables x and x1 and x2, if I wanted to write in terms of a matrix format, how how should I be able to write it down? That is the thing, right? So let's try to see that. Can I write this x as, okay, first of all I'll define what is x. So previously I have defined z as what? A vector containing this uh, random variables, right? Z1 and Z2. Now I define the vector x as x1 and x2. Is that okay? It's again the vector of these two. So if I wanted to write this x in terms of z in a matrix, vector matrix format, how will I be able to write it down? So if I write like this, 1 and 0, which is 1 basically for this one, and 0 for z, right? And row and root of 1 minus row of
Square, right?
uh, z1 and z2, right? And here if
1
I,
minus row square.
sorry, so it should be row square, and this is x1 and x2. Is that okay? Now if I write in this format, they will represent the same thing, right? Here x1 equal to z1 and x2 equal to this one. Is that fine? I think it is fine, right? So I can compactly write this as x equal to 1, 0, row, root of 1 minus row square of z. Fine. Uh, if you think it carefully, the joint density of these two random variables, it is known to me. Or do we know the joint density of this z and or x? What is known to me? Okay, will state that z1 and z2 are independent of each other. So we know this one, right? Why we know this one? Because we know that z1 is a random variable, which is standard normal. Z2 also is standard normal random variable, and if they are independent of each other, uh, will I be able to calculate their joint density? Yes or no?
Yes.
Yes, right.
Yes.
uh, so the question here is, I know fz of z, right? So what is fz of z? Basically, if I, okay, I'll write it down here. What is fz of z? And that will be equal to 1 upon 2 pi, right? 1 upon 2 pi e to the power minus maybe half z1 square plus z2 square, right? Correct, right?
So sigma by 2, 2
What
pi
is,
part sigma by 2.
where sigma by 2? Here. But let's say we have said that, right? So Z1 and Z2 are what? So
Standard norm.
standard normal, right? So if they are normal means standard normal means their
Zero and
median
Yeah,
is zero
mean
and
is zero.
variance is one, or standard deviation is one. So like this, right? Like this.
yeah, d by 2 only. You are
D by
taking.
2. So D is
It's
what?
just one, huh?
D is
D
These
is
two na
single.
two.
Yeah,
D is
okay.
the
It's
dimension of
single.
this vector, right? So in this case, the dimension of this vector is 2. So it is 2 pi, right? And can you see that this z1 and z1 square plus z2 square is actually is what? It's the length of the vector z, right?
It's not square of them.
Or square of the vector, right? Norm.
Length square.
L2 norm, let's say. So I can write this as like this: 1 upon 2 pi e to the power minus half norm of z square, right? Fine. So that is fine. Okay, but the question, the thing is, this is known to me, correct? This is known to me. Now I need to find out the density of x,
Sir,
which is unknown to me, right?
sir.
Yes.
This is a very basic question.
Sure, sure.
Trying to recall, yeah, stats too. See this FZ, right? That is supposed to be the PDF of a normal distribution, right? Is that,
Mz, this one.
yeah, yeah,
uh, okay, you are correct. So let's say if I say only z1 is my, okay, I'll just write, okay, we have the space here, maybe I'll just, okay. So let's say z1 is normal 0 comma 1, right?
yeah.
What is the, so what is the PDF of this z1?
1 by 2 pi.
1 by so I'll write like this: fz of fz1 of z1 equal to 1 upon root 2 pi, right? Root 2 pi sigma, right? Are you able to recall this?
Yeah, yeah,
Root 1 upon root 2 pi sigma, basically here, right? uh,
yeah.
Into e to the power minus z1 minus mu whole square upon 2 sigma square, right?
Mm, yes.
And this is what, this is my mu and this is my sigma square.
Yeah.
So that means mu is equal to 0 and sigma square equal to 1. And if I plug in those values here, what should I get? 1 upon root 2 pi, because sigma is 1, right? And
Yeah.
e to
Sir,
the power,
sigma should be outside the square root, right? Because if it's inside, it will be sigma square.
okay, yeah, that's correct. Yeah, that's correct. It should be root 2 pi sigma, yes. But still, it's going to be 1. So it will be 1 upon root 2 pi here. And here, what will be, it is z1 square upon 2, right? Because mu is 0 and sigma square is 1. Is that okay?
Yeah.
Right. Suppose there is another variable which is z2, correct? And it is also normally distributed with mean 0 and variance as 1. What will be joined, oh sorry, what will be the PDF of it? It will be, again, it will be
1
like this:
by
1 by root 2 pi e to the power minus
Z2 square by 2.
2. Correct. Right. Now let's say this z1 and z2, these both random variables are independent of each other, correct?
Yeah.
So how does their joint density will look like? So it
Yeah.
will
It's the product. Yeah.
be z1 comma z2, right? And that will be the product of this. Can I write like this: 1 upon root 2 pi e to the power minus z1 square by 2 into 1 upon root 2 pi e to the power minus z2 square by 2, correct?
Yeah. This is where I had the question. Yeah. I'm so sorry that, I messed up. This is supposed to be joint
This is joint.
distribution. It's a
Yeah.
product of marginals, right?
Yeah. Basically, these are the
So,
marginals. So these PDFs, right? If you consider the marginals in case of multiple random variables, if you try to look them in a joint scenario, right? Joint density
mhm,
scenario, this marginals basically will become the the PDFs only, the PDFs of that single random variable.
Okay, okay. Maybe
Fine.
that is what I missed. Okay.
Yeah. So it is because how do you find out the marginals generally? In let's say in the simple case of PMFs, right? So suppose I think it is like very clearly understandable here. Suppose you have the probability mass functions, right?
Yeah.
Let's say there are two variables, x and y, right? And let's say x takes values 0, 1, and 2, and let's say y takes values 1, 2, and 3. And suppose the probabilities are given to me like this point. Okay, maybe I'll just take a smaller, right? Smaller box so that it will be easier for me also.
Yeah, I get it. We added, right? For one of the variables.
Yeah, so what will be there? Like point 2, point 3, point, let's say point 4 and point 2, right? These are joint densities, right?
Mm.
But how to find out their marginals? So if y of y, if y of 1 will be
0.4.
0.1 plus 0.3, right? That means, but what is that exactly? So what we are doing it here is we are summing over this values of random variables of x, right? All random variables of x, correct?
Yeah.
Similarly, you do integration also. If when you find out fy of y, right, you actually take the integration over the values of x, right? and
Yeah.
and you,
Mm.
and you sum this joint densities, I think, right? uh, for I think x to find out. So actually you integrate, you treat y as constant, right? Because for
Correct.
that
Yeah.
value of y, you actually take the sum, or you integrate over the values of all values of x, and that eventually you will be getting the same PDFs only, the, as you take it for individual thing.
Okay.
Yeah,
Yeah. Thank you so much, sir. Yeah.
got it. Yeah.
Yeah. Yeah.
So and then I think then it will be the easier thing, right? So it is 1 upon 2 pi square, right? Is e to the power minus z1 square by 2, or minus z2 square. So I think if I take minus half common from here, take minus half common, then it will be z1 square plus z2 square, right? And this 2 and this root will be like, we'll get only 1 upon 2 pi. Okay, that's fine now. Okay, so x is equals to so I this is known to me, right? Now what is unknown to me? The joint density of x1 and x2, right? Okay, that is my goal now, to find out what is the joint density of x1 and x2, right? Okay, now treat this as, this is a matrix, right? Let's say this matrix is A. Okay, uh, now then how will I say that this z will be looking like? So z equal to, if I wanted to find z, uh, how does it will be like? So now the equation is like this: x equal to az, then z will be a inverse x, right? This is a vector matrix format, or you can say that it's a matrix format. Then if x equal to az, a is a matrix here, then z will be, we cannot have x by a, because in matrix we cannot divide by the matrix, right? You will take its inverse. So z will be a inverse x, correct? Okay, I hope all of you know that. uh, let me okay, we'll try to see some properties here, uh, which will be like, I think we'll be putting all these properties later on into the derivation. So we'll see the properties of A first, okay, the matrix A. So
Sir,
yeah,
where from where you get this here?
here, right? So
What is x? Oh,
so
this is yeah. Okay,
so
okay.
this was x1 equal to z1, x2 equal to this one, and I have written this x1 and x2 in the matrix format, right? And when we write this, then it was A. Fine.
Okay, so A is the coefficient matrix.
Yes. So now we'll see some of the properties of this matrix A. What will be the determinant of A? It is
Square root of
1 minus rho square, right? Okay. What will be then if determinant of A is this one? Then what is the determinant of A inverse?
1 by root over
1 by
1 by
root over
1 upon root of 1 minus rho square, right? So that we know. Now let us say we know that x1 is equal to what? Z1, and x2 is equal to rho z1 plus root of 1 minus rho square into z2. What is the expectation of x1? So okay, so
A into expectation of Z.
x1 is equal to z1 and x2 is equal to rho z1 plus square root of 1 minus rho square into z2. So if I wanted to find out what is the expectation of x1, what then it will be
0.
expectation of z1, and that is equal to 0, right? Right? Okay. Similarly, what is the expectation of x2? It is rho into expectation of z1 plus root of 1 minus rho square into expectation of z2. But the expectation of z1 and expectation of z2, they are both 0, right? So expectation of x2 will also be equal to 0. All of you agree with that? Right? This is going to be 0, this is going to be 0, since both of them are the standard normal, right? So the mean of z1 and mean of z2, that is equal to 0, and that's why expectation of x1 is also 0 and expectation of x2 also is 0. What can we say about the variance of x1? Variance of x1 is equal to variance of z1, and that is equal to
One.
1. What about variance of x2? That is equal to rho square
Goes
variance of z1 plus 1
root
minus
over
rho
1
square
minus. That's it. 1 minus x.
into variance of z2, right? So rho square and variance of z1 is 1 plus 1 minus rho square into variance of z2 is again 1. So that is equal to 1, right? Fine? This is okay? Okay, I hope this is fine. Um, Next step is what? Let us try to find out what is the covariance between x1 and x2. Okay. So covariance between x1 and x2 will be equal to uh, expectation of x1 into x2. Why? Why this formula is correct?
So it's expectation of x minus expectation of x1 minus expectation of x1 and
Yeah.
x2
Okay. This is your
minus
formula, right?
expectation.
Yeah. This is your formula for covariance, but they are 0, right? We already have found out above the expectation of x1 and expectation of x2 is equal to 0. So that is going to be 0 here. Uh, Fine. And now then what we should do? What is expectation of what is x1? Z1. What is x2?
I said this were
2
independent,
Z1.
right?
Hmm?
These were independent, right?
Which one? X1
X1
and
and X2.
no, we don't know, right? We know that Z1 and Z2 are independent. We
X1.
don't know about x1 and x2, right?
Okay.
Correct.
Expression of
When we say that they are independent,
Covariance
When the
is
joint,
They are
density is equal to the marginal product.
that is also there. Another is if the
uncorrelated.
covariance between these two, right,
covariance
is equal to 0. If the covariance between these
0.
two variables equal to 0, then we can say that they are independent, right? So we need to find it out whether they are independent or not. So now, okay, x1 equal to z1, and what is x2? x2 is equal to rho
Z1.
z1 plus root of 1 minus rho square z2, right? And if I just multiply this, then it will become rho z1 square plus root of 1 minus rho square z1 and z2, correct? Until this part is fine. And if I can now you know take this expectation inside this bracket, and that will look like rho into expectation of z1 square plus root of 1 minus rho square expectation of z1 into expectation of z2. I can write this because z1 and z2 are independent, correct? Is that fine?
Yes.
Yeah. So now expectation of z1 and expectation of z2, both of them are 0. So this is going to be 0, right? Is going to be 0. Fine. Now what about this part? Rho expectation of z1 square. Is this going to be 0 or not?
You can find from the
Sir,
variance.
Yeah.
what's the variance of Z1? Can you provide?
What is it? Sorry. What is your question?
A variance of Z1 is just 1, right?
Variance of z1 is 1. Yes. Yes. It is equal to 1. We already have, we know, right? Because z1 and z2 are the standard normals. They have mean equal to 0 and variance as equal to 1. We have started with this, right? So that is equal to 1, but we need to find it out. So we know one thing from stats is that variance of let's say z1 equal to what? Expectation of z1 square plus, or not plus, minus,
So it should be 1 expectation of Z1 square.
minus expectation of z1 whole square, right? Okay, so now I wanted to find out this part, expectation of z1 square. So what is that? Then expectation of z1 square will be equal to variance of z1 plus expectation of z1 whole square. What is expectation of z1 square? Or expectation of z1? 0, right?
0.
So this is going to be 0, and then variance of z1 is equal to,
1.
so then expectation of z1 square will become 1. And if I plug in this value in above this equation, what I'll get?
Rho. Rho.
Rho. So the covariance of x1 and x2 is equal to rho, right? So can you say that x1 and x2 are independent?
No.
No, right? Because they will be independent only when the you can say that when the
Rho is
covariance
0.
is equal to, yeah, fine. So let us summarize all of the values we have seen so far. What we have seen is expectation of x1 is 0, expectation of x2 is 0, expectation of x1 is 0, expectation of x2 is 0, variance of x1 is 1, variance of x2 is 1, and the covariance between x1 and x2 is equal to rho. Fine. If I wanted to formulate a covariance matrix from this, what that will be? The covariance matrix between x1 and x2, or okay, not, let's say covariance of x. What is x? X is a vector which is x1 and says x1 and x2. So let's say what is covariance of x is, that is equal to,
Row
here it will be
1.
1, right?
1.
Variance of
1
x,
row, row 1.
1 row and 1. This is what? This is the variance of x1. This is variance of x2, and this is covariance between x1 and x2. And we know the covariance matrix is a symmetric matrix. So I can say that the this value also will be the covariance of x1 and x2. Fine. Let us call this matrix as sigma. Fine. Let's say this is a sigma matrix, and you can show that sigma matrix is equal to A transpose. What is A matrix here?
Coefficient matrix.
Yeah, this matrix, right? We initially started with this matrix. So the covariance matrix which we have found out here, right? This is actually equal to the this matrix A transpose. You can show that anytime. So you can easily can show that, and that will be equal to this covariance matrix. Let us say this covariance matrix X I denoted by sigma, because that's how Sir has denoted there. So let's say this is sigma, right? Now, what is the determinant of this matrix? Determinant of sigma is
1 minus rho square.
rho square, 1 minus rho square, right? And now, what is the uh, inverse of this matrix? So, sigma inverse is equal to 1 upon determinant into the cofactor matrix, right? So this will be 1
1
minus,
minus rho minus rho.
right? This is correct, because if you have this, so if you select this one, it will be 1, right? Then 1 will come here. If you select this one, row will come here, but with the minus sign, because it will be minus 1 to the power 1 plus 1, right? Because no, 1 plus 2, so that will be minus 1, so minus of row. I hope all of you know how to calculate the inverse of a matrix. Fine. So all of these things are there. Now I just wanted to find out what I just wanted to uh, find out the joint density of X. So we have seen that how to find out the joint density of X. If I know the joint density of Z, the formula is Fz of Z, right? Fz of Z into determinant of Jacobian of basically, or determinant of Jacobian, right? So in this case, the Jacobian will be this one. Why I will not explain it here, but let's say this determinant of A inverse. Now, this fz of z is what? What should I? We have seen that, right, initially. Uh, okay, maybe I'll show you there that part also. This is what we have said initially, right? X was equal to az, and then what about z? Z equal to a inverse x, right? Is that okay? X equal to az, and now z is equal to a inverse x. I hope this is fine. And if I wanted to find the joint density of x, uh, basically what is this? This is basically it is like this: f of x1 x2 of x1 comma x2, and that is f z of, instead of z I'll write a inverse of x into let's say into mod of determinant of a inverse. Okay, now what do you what is the density of this? How should I write the density of this? Is equal to 1 upon root 2 pi. Okay, 2 pi only, right? Not root 2 pi. 2 pi e to the power minus uh, minus half norm of a inverse x square, right? And what is determinant of a inverse? It is 1 upon square root of 1 minus rho square. All of you are fine with this part? If you don't understand, let me know now. Is this okay? Yes or no? Okay, fine, right? What I haven't done anything different. I just plug in all the values. Z was equal to A inverse of X. F of Z already we have said that this is the density, right? 1 by 2 pi e to the power minus half norm of Z square. I just plug in A inverse of X instead of Z there because I know the joint density between Z1 and Z2. And determinant of A inverse we have already calculated. It was A inverse. I'll show that to you as well. Think we have, yeah, here itself we have calculated that. And so all of things we have now calculated at one place, and we have come up to this equation, right? Now let us say, what is this equation now? It has become fx of x. When I say fx of x, what does it mean? It's a vector of x, right? Those transforms, simple transforms we have done. Then this is going to be 1 upon 2 pi root of 1 minus rho square into e to the power minus half of A inverse of x square. Okay, done. Now this A inverse, how can I write it? Or maybe this norm of A inverse of x, right, a square. How can I write it down? So I can write this in a matrix format as like this. Let's say, yeah. Can you tell me if you know? It's fine. If you don't know, that's okay.
Transpose in transpose.
Yes. So it will be x or okay. Do I need to? Okay, maybe I'll write down here in this side like A inverse of x transpose inverse of x, right? And if I further say, like simplify it, how does it look like? It will x transpose
X transpose.
A inverse transpose A inverse of
A
x, right?
inverse. Yes.
Correct. So I'm putting this here uh, without explicitly writing the steps. So maybe I'll just circle it around here. So 1 upon 2 pi square root of 1 minus rho square e to the power minus half. Uh, it is x transpose A inverse transpose, sorry, it's, x transpose A inverse transpose A inverse x, right? Fine, this is okay. What about this A inverse transpose into A inverse? uh, can I write it like this? 1 upon, let's say, 2 pi root of 1 minus rho square e to the power minus half x transpose. I can write this as A inverse, or not, because they are A inverse transpose into A inverse, right? I can write like as like this: A transpose inverse of x. Fine, this is okay. This part I have written it like this. That's fine.
Yes, sir.
Okay. But I said earlier, right? This covariance matrix is actually A transpose, correct? And then what is A transpose inverse? Is basically the covariance matrix inverse, right?
Yes.
So can I directly put the value of covariance matrix inverse there, and let us say how does that will look like? So it will be 1 upon 2 pi root of 1 minus rho square e to the power minus half, right? And x transpose is what? It is basically x1 and x2, right? This inverse will be 1 minus rho 1, and x is x1 and x2, and one more thing is remaining is that 1 upon 1 minus rho square, this constant, right? So this is everything will go into the exponent of x. Is that fine? I hope that's okay. That is not a problem there.
Sir, can you see your reactions?
Huh? Sorry?
Like, can you see your reactions?
No, I don't understand. Where is the issue?
Like you are asking now, is this fine?
Ah,
So
okay,
can
okay,
you
okay,
can you see our reactions?
okay, okay. But I generally I won't be seeing because I shared the screen, right? Okay, okay, got it, got it. Sometimes I look at that. Okay, I hope okay, that's fine. So this is what your density will look like, right? Uh, Actually, see, I think this okay. This one thing is fine. You actually can do one thing is that you can solve this, like you can solve this matrix out, and what you will get if I solve this matrix, then I'll get I think 1 upon 2 pi 1 upon 1 minus rho square. This part is not much important as far as the even
Exam.
the syllabus, yeah, exam also is concerned, or even the syllabus also. But you should know this. If I just you know f- uh, take the multiplication, what I'll get is minus rho square, and if I just do the multiplications, right, I think I'll get a, because this is a 1 cross 2 vector, then we have 2 cross 2 matrix, and then 1 cross 2 cross 1, right? What will be the product of this? One
Scalar.
scalar, right? So, and
Scalar.
that scalar is basically I'm writing it down here. It will be x by x1 square plus let's say it is x1 square by my thing. Okay, maybe I'll just write everything out. You may check cross check later. I'm just writing down directly what is coming out here. It is x1 square plus uh, minus of rho upon root of 1 minus rho square plus x1 plus rho by root of 1 minus rho square x2. Fine. That's how it gets, and square of it, square of this term. Uh, this you will get fine. And if you just simplify it further, right? I think simplification is given in the lectures. You can find it out later. The simplification says like this, that your joint density of f of x is simply equal to fx of x1 or fx1 of x1 into fx2 given x1 of x2 given x1. So what does that mean? It's a product of uh, the marginal density and the conditional density, right? So the joint density of x, right, it is a product of the marginal density and the conditional density, and I think it is true for every cases, right? uh, we already have seen that also previously. The only thing is what will be the distribution of this. What is the distribution of this? So what is the distribution of x1? It is normally distributed with mean 0 and variance 1, correct? You have seen that, right? And the distribution of this is normal distribution with okay, x2 given row x1, and the variance is 1 minus rho square. Okay, so this is going to be or I sorry, not x2 given, I think you can say that is this sorry, the conditional distribution of x2 given x, okay, I'll write down it properly. So the conditional distribution of x2 given x1 it follows normal x1 equal to some x1 follows normal rho x1 as rho square. Fine. uh, if you don't understand this part also is fine, there is also no issue, but this is what it is. I hope you understand the derivation till this part, and that is what we are going to continue in the next understanding of whatever the properties of bivariate normal and multivariate properties. We'll look into that, and we'll see the
So,
questions based on that. Yes.
so the resultant is also a normal only, right?
Yeah, resultant also is normal. See, because we have seen that, right? So these are x1 is also a linear transform of normal distribution, and x2 is also linear transform of that, right? And if you
Right.
take a joint density of that, that also is coming out to be normal. Fine. So it will also be it should be a normal density basically. Okay, let's say we'll see the what we have seen about the bivariate normal till now. Bivariate normal. Uh, so the bivariate normal is x equal to az, and fx of x is equal to what? We have seen the density as fz of a inverse of x into mod of determinant of a inverse. Okay. What was the covariance matrix? Covariance matrix denoted by sigma, and that was equal to that is similar to A transpose, and uh, we have said that this is a covariance of X, right? Then we have seen one more property of it as determinant of A inverse, right? So determinant of A inverse was what? It was, I think it was 1 upon root of 1 minus rho square, right? And that is again is similar to determinant of this covariance matrix. So I can write the determinant of covariance matrix as same as that of determinant of A inverse. Correct? So I think I will show you that part also, where we have found out determinant of this sigma is 1 upon, sorry, determinant of covariance matrix is 1 upon sigma square. So if I wanted to find determinant of A inverse, what that will be, this is 1 upon root of 1 minus rho square. So I can put instead of 1 upon 1 minus rho square as determinant of covariance matrix. Okay. So if I put that thing into the joint density, so the joint density will become like this: fx of x equal to 1 upon root 2 pi, or okay, not root 2 pi, it is 2 pi because it's a joint density. So it is 2 pi square root of determinant of sigma, fine, into e to the power minus half, what was it, x transpose sigma inverse
Sigma
x,
inverse x.
right? Fine. So this is what my density look like. Fine. So now the matrix which you have started with, right? uh, that matrix was like the matrix A, or we have said that this diagonal matrix I can, or the covariance matrix I said, this is equal to A transpose, and if I, my A is equal to 1 0, 1 0, and what was it? I think it is rho and square root of 1 minus rho square, right? It was a simple linear transform. But suppose if I wanted to make it generic matrix, right? So if any kind of linear transform I can take, what that will look like, then my matrix sigma, the covariance matrix will look like this. Okay, before that I'll write sigma as, if my matrix A is like this, what is my sigma? Sigma will be looking like I think it is 1 row, row and 1, correct? That was my sigma. But in general, I can say that for any kind of linear transform between z1 and z2, right? If I wanted to take different transforms, then it will look like row AB. Here it will be row AB, and it is going to be b square. So what does that mean is that, let's say if my x1 is equal to, let's say, a uh, what is it, a square, not a square, let's say a z1, right? And let's say x2 is equal to, uh, suppose this row or b row z1 and plus root of 1 minus rho square z2, like that, something like that. Or maybe I just multiply here z2 and here a, right? In that case, so whatever the linear transform you want to take, any kind of different values if you want to take, right? The generic formula for this z1 or this covariance matrix will be like this. And if I use that, then this will be my sigma and this will be my joint density, right? Okay. Now, one more thing I think we haven't seen is, or we have seen this derivation only for x equal to az. But what if I wanted to add some constant here? Let us say some constant is c, right? Az plus c. In that case, what will be my z? Because previously I had x equal to az, then I said z was equal to a inverse of x, and based on that we have we have found out this joint density. But instead, if x is equal to az plus c, then what will be my z? Z will be equal to a inverse x minus c, right? Correct. Right. And whether the sigma will change or sigma will remain same, sigma will remain same as A transpose. Oh, right? Then the joint density will look like this: 1 upon 2 pi determinant of, determinant of sigma, or mod of determinant of sigma, uh, e, e to the power minus half. Instead of x transpose, it will be now x minus c transpose. Fine, x minus c transpose sigma inverse into x minus c. That's going to be my joint density in case of a bivariate normal. Now, suppose whatever we have found out, right? If I wanted to translate it to the multivariate normal, what do you mean by multivariate normal? If I have d such uh, variables, right? So previous, I think initially when we have started today, I have shown you that, let's say z1, z2, we have d such normal variables, right? z1, z2 to zd, and we have found out. So we know their, let's say we know their joint densities. Then how do you find out their, and if I wanted to find out the linear transform, okay, or linear transform between all of these random variables, right? The d random variables. In that case, uh, how this linear transform will look like. So in, let's say, if that is x equal to az plus mu, but here x is what, in rd, z also is in rd, right? A is a uh, d cross d matrix, right? A should be a d cross d matrix. Mu is a vector. In this case, it will not be a constant, and it will be a vector of d cross 1, right? Now, if x equal to az plus mu, then the joint density of this will look like what? Fx of x will be equal to 1 upon, will it be 2 pi or will it be 2 pi to the power d by 2? D by 2
Divide.
and square root of, again this is same determinant, mod of determinant of sigma, and then e to the power minus half, what is that here, x minus mu transpose sigma inverse x minus mu, right? This is going to be the joint density. And finally I can say about, by looking at this joint density, this looks like a normal density only. It is normally distributed with what, mu, and the variance will be a covariance matrix. So this is going to be a covariance matrix. this is a vector of sorry, p cross 1. I hope this is fine. Till now, this is no issues. Fine. So if this is a setup, right? Now we'll try to see the properties of this multivariate normal. Now we'll see the properties.
Sir, you are not audible.
Yeah, I'm not speaking. So suppose x is distributed like this, normally distributed with mu and sigma, right? X is what? X is when I say x is normally distributed with mu and sigma is x is actually a uh, it's like it is a combination of all the normal all the linear transforms of the normal variates, right? If that is there, and then if I define a new random variable y such that it is equal to a transpose x, okay, a transpose x, and what is a here? A is a some vector a1 a2 like that, let's say a t, and it's a vector of constants, fine. If a transpose x, then what will happen to the, or what will be the density or distribution of y? So x is this distribution, y equal to a transpose x, then the distribution of y will also be a normal, right? What will be the mu? If you just apply the normal formulas, right? What is expectation of y equal to a transpose expectation of x? What is expectation of x? Mu, right?
Yeah.
So then what will be the in this distribution? It will be a normal distribution with mu as a transpose mu, and what will be the covariance? Will be a transpose sigma a. You can show that also here, because if you just apply here, right, it will be variance of y equal to a transpose square, right? So basically, if I wanted to square it, it will look like this. So it will be like kind of like this. Variance of x into a. So this variance of x will be a, it's not variance of x, it will be a covariance matrix. So it will be covariance of x. Fine. So this is going to be its distribution. Suppose y is another random variable which is equal to bx. In this case, p is another matrix, right? B is some matrix. In this case, what will be the distribution of y? We'll look at the examples, right? Okay, we'll see the examples, and I think after looking at the examples, you'll be able to appreciate what is happening here. In that case, y is normally distributed with what? B mu. It is again same logic. If you apply the properties of expectation, it will be mu B mu, and what will be the covariance matrix? It will be B sigma B transpose. The difference between these two is A transpose, it will come this side, and so this is because uh, it is due to the fact that how these vectors and matrices are multiplied to each other. Because of that only it is coming the difference like that. Okay, I hope this is fine. uh, till now, if that is okay, we have left with one more concept of, I think, parameter estimation. But before that, we'll see some examples for this topic. I'll give you some examples. You try to solve these examples. Okay. Any doubts till now? No, right?
Sir, just wanted to ask you something.
Yes, yes.
Sir, like whenever we find, covariance X and Y or correlation X and Y, right?
Yeah.
So basically, uh, in case if we are getting zero, say for example,
Huh.
in this case, sir, actually this covariance X and Y or this correlation X and Y, it only gives a detail about the linear relationship, right?
Hmm.
So
Correct.
we can yeah. So basically, if it is zero,
Huh.
it is not necessary that they will always be independent. So there might
Yes,
there
yes,
might
that's
be some
the same doubt I have. Okay.
other kind of relationship also. This is what I thought of asking you.
Yeah.
Yeah, yeah, okay. So
The independence implies uncorrelated, but it's not. The
Yes,
converse is not.
yes, yes.
right, that is correct. But let's say, I think that is again that property. I think sir has also mentioned. I think the third property, right? Lectures also. Let's say xi and xj, right? What is xi and xj? Two, uh, two random variables, right? If they are independent, uh, in this case, the covariance between xi and xj uh, is equal to 0. Fine. That is okay. This is fine or not?
Yes, yes, yes.
Right?
Yes, this is fine. Correct, correct,
Yeah.
correct.
But if let's say the converse, right? Converse in general case, the converse is not true. But in
Not
the
true.
case of multivariate normal,
Okay.
with the
It may or may not be true.
yeah, in okay, in other cases, right? Another cases, if the covariance between the two variables, right, x1 and x2, if that is equal to 0, we cannot say that they are independent or not. That is correct,
Correct,
because in that case the converse is not true. But
correct.
if it is a multivariate normal case, in that case this is also true.
Okay. In case of multivariate normal, so it's basically bidirectional.
It is
It goes
bidirectional.
both way.
Yeah.
Okay, okay.
But if it is another case, let's say x is some other, let's say x is exponential distribution and x1 is exponential and let's say x2 is uh, some normal distribution. And if I wanted to find out the covariance between them, and we have found out that covariance is equal to 0, right? Then it doesn't translate it to that they
Independence.
are independent. Yes. Okay. That's fine now.
So if in case if one is independent and one is some other kind of distribution, then it's not necessary,
Yes.
basically.
Yes. But this direction is true for all. If they are independent, right,
Ha ha, this is understood. If they are independent, then definitely it will be
the
zero.
covariance is going to be 0. But other
Covariance
around,
correlation.
yeah,
Yeah,
otherwise it is not. Okay.
it has to be checked. It will be
Yes,
conditional, basically.
yes, yes, correct. So here I can actually show you some examples. These are from week 11. Maybe how to find out. We can look at it. But before that, I wanted to say. So I'll share this also with all of you so that you can practice later on about the Chebyshev inequality and okay. So this is the question, right? Uh, uh, if y follows the normal distribution and where is y is a vector of y1, y2 and mu is 3 comma 1, 3 1, and this covariance matrix is given to me. Find the distribution of y1. That is the question. You guys can try for maybe solve for 2 minutes and we can see the solution later on.
Sir, please do share today's approach.
Okay, is it done? Uh, are you able to solve this problem? Yes. Okay. What are the answers? Okay. You didn't write the answers. Fine. Okay. Maybe I'll solve this. Uh, what is given to me is, let's say, y follows this normal distribution, right? And y1 is equal to this, and mu is equals to this, and then I need to find out its distribution. It is pretty simple, right? What is the distribution of y1? Mu will be 3, right? And the variance will be 6,
6.
right? So the option A will be the correct option. Correct, right?
Yes.
Okay. What about the distribution of y2? It is again 1 and 13. But what about the distribution of y1 plus 3y2? So the question here is this one. Then mu is 31 and sigma is given as 6, 1, 1 and 13. And y is distributed as normal, mu and sigma. Given, I need to find out what is y1 plus 3y2. The distribution of y1 is normal distributed with mu 3 and variance as 6. Y2 is the distribution is normal, mean 1, right? So this mean 1 and the variance as 13 there. What is the distribution of y1 plus 3y2? So can any of these properties is applicable here? Okay, let us try to see that. Okay, this is y1, this is y2, right? This is vector of y. This vector y, which consists of these two random variables, which is y1 and y2. How will you write this y1 plus 3y2? I can write it as like
1,
1,
1,
3,
3, y1,
y1, y2. So if I say that it is A transpose, right? A transpose, because if I just multiply this will give me y1 plus 3y2. So if I say this as y A transpose of x, then what will be the distribution of this random variable?
transpose sigma A.
Hmm? Then the distribution of this will be it will be like normal A transpose mu,
Transpose mu.
that is the mean, and then A transpose sigma A will be the covariance, right? Or the variance. So what is A transpose mu? A transpose is 1, 3, because A is equal to 1, 3, the coefficients. Mu is given to me as 3, 1, 3, 1. So the the mean will be 6, right? And the variance will be A transpose sigma. Sigma is 6, 1, 1, 3, 6, 1, 1, 13, and A is 1, 3. So that will be 1, 3, then 9. 1 plus 13 is 16. That's going to be 9 plus 48. How much?
129. Oh, sorry. 9 plus 6, 57.
So the distribution of y1 plus 3y2 is what is normal with mean 6 and
It should be 40, right? 940.
how come 40 this
Yes, it will be 9 and 40.
9 and 40, no? 1 plus 39, right?
9 plus 1 1 plus 39
No, no,
Yes.
no.
no
Yes, 1 plus 39, right?
6 plus 3 and 1 okay
The last row and to A.
okay fine, fine. So this is wrong, huh?
It should be 129.
Is 40, right?
Yes, that is 40.
And then it will be like 9 plus 120, so it is 120, correct? Yeah, sorry. So this is the distribution. So I think if that question is there, so which one is the correct answer here?
First option.
Option A is the correct answer, right? Okay, maybe we can see some of the problems from Chebyshev inequality. You remember Chebyshev inequality and Markov inequalities or no? Do you know the how to find out the maximum likelihood? This method, you know it. Maybe I'll just describe it in a bit, and then maybe we can see the solution for that. Let's say, okay, what is that maximum likelihood method is used for? I hope you understand the problem, right? There, the problem, how to solve this, how to find out the distributions, given that uh, we may see some problems from the previous years, maybe during the revision session, or if you have any problems, you can tell me. We can solve that also.
Sir, it is used for parameter estimation.
Which one?
Maximum likelihood.
Yeah, maximum likelihood. So there are several methods for parameter estimation, right? And these are very useful methods while you go through like maybe the next courses, maybe machine learning techniques. I think deep learning also you can encounter, but mostly you can say that this is the very important uh, concept of parameter estimation. What were the techniques we have seen for parameter estimation in stats 2?
Bayesian.
I think we have learned about MME, method of moments estimator. Then we learned MLE, which is maximum likelihood estimator, and another one we have seen is Bayesian.
Bayesian.
Yeah, Bayesian estimator. Uh, for this course, we will be learning about maximum likelihood estimator, right? And why we need this likelihood estimator methods, like or why we need this estimator methods? What is the idea behind those, and why we? Okay, what parameters we are going to estimate?
That we find the maximum likelihood and the function we find and will optimize it.
Okay, no. The what I'm saying is we are going to look at this parameter estimations for what parameter we are estimating here. So okay, I'll just give you the example of it. Let's say you have human.
Sir, it depends on the distribution, no?
Yeah, that is okay. But let us say you have a population, right? And okay, or maybe you can say that whatever the data you are collecting, right? That data is a sample coming from a large population. What we are assuming is that this data is coming from, or this sample is actually we have collected from a some underlying population distribution. We and any distribution, right? Any distribution which we look at, right? It will have some parameters, but from the sample we will not be able to tell about the parameter exactly, right? So these methods will
So,
help
bas-
us. Yeah,
so basically, that parameter basically helps us in identifying the probability of observing the sample.
correct.
So what is the maximum probability that this sample will occur given the parameter,
This is
given the
maximum
value of that
likelihood
particular
estimator.
parameter.
Yeah, this is the maximum
Yes.
likelihood estimator. So the parameter actually is from a. So what we generally do is you you accumulate some data, right? So let's say housing price prediction example, you have seen that, right? So this whatever the houses you have, the data you have collected, that is not the entire data of the houses, right? It's a sample, right? from
Sample.
from the like large population, and you may not be able to uh, collect all the data of the population, right?
So we estimate the population
Correct.
data. No?
Parameter. We estimate the parameter of the distribution, because all of these parameters, they define the shape of the distribution, right? They define the shape of the distribution. They define
Yes, yes, yes.
how it is varying, right? And from there, if I know that those parameters, I'll be able to calculate the probabilities of uh, uh, very easily, right? So that is the idea behind it. So in statistics, we have seen that x1, x2 to let's say xn, these are the samples, right? If they are coming from some IID distribution x with let's say some parameters theta, theta can be it's a group of parameters, maybe more than one parameters, right? Then what you do is you try to find out their likelihood. So likelihood of theta, right? So this is called likelihood. Likelihood is what? Basically, it is the probability of observing this sample, right? X1, x2 to xn, given the parameter theta. So, given that parameter theta, what is the probability that uh, this sample you can see, right? So, in that case, because okay, I think I will not go into the stats details, but yeah, so that will be basically it is the product of I equal to 1 to n. We anyway we will learn about all of this again in MLT if you have not done MLT already. So it is been there discussed properly. So this is fxi of xi given theta. So what is it fxi of xi given theta? It may be the probability mass function or probability density function. So
It's the prior distribution.
not prior distribution. It's not prior distribution. Prior distribution is a
Okay,
different case. Prior distribution
yeah,
we
that's
use
the difference.
Bayesian estimator method, right? In prior
No,
distribution,
yes, sir.
we know
Yes.
that how
Bayesian
this
estimation.
yeah. So prior estimator is actually prior is actually for the parameter. So we know something about that parameter from the experience or from or you have the data supporting to that, right? This is not the prior distribution. This is just likelihood that whatever the probability density function or probability mass function is there, we take a product of it, and that is exactly the product of all of this is equal to the likelihood, right? And for the simplification purpose, what you do, you take a log of that, log of a likelihood, and then this product will become the summation, right? Sum of I equal to 1 to n xi of I xi theta, right? Or not fxi exactly, it will be because when you take the sum, right, if it is exponential, then some let's say p of theta, right? You need to maximize this, or in another way what you can do is you can take a negative of this log likelihood, fine, and you try to optimize it. So optimization means what, like you can either maximize or you can minimize it. So if I take a log, this problem of maximization become equal to the problem of minimization, and in that case what you do in minimization case, you let's say this is h of theta, and let's say entire thing. So I'll take the differentiation and equate it to 0, and then find out the parameters from there. Okay.
In maximization also we follow the same procedure.
Yeah. Maximization. Then what you do is you don't take the
Positivity.
yeah. It will be the positive. Fine. So can you just for this example, can you just try to find out what is the answer? I will show the steps again how to solve this, but try to. Anyway, the answer is already there. You can, or maybe I can just solve it. That's okay. That's fine. I'll do that. So suppose the lifetime of a bulb is exponentially distributed with parameter lambda. What does that mean? Uh, the x1, x2. So the question here is x1, x2, xn. These are the IID samples. They are coming from a exponential distribution with parameter lambda, right? We randomly test 5 bus and found their lifetimes as this. Find the maximum likelihood estimator of lambda. So what samples were given to me? So 3. So x1 equal to 3, x2 equal to 2, x3 equal to and x5. These are the 5 samples given to me, which is 4, 5, 6, 4, 5, and 6. Right? These are the samples given to me, and I need to find out the estimator for this lambda based on the given sample. So what should I do first? Okay, what is the PDF of this exponential distribution? Lambda e to the power minus lambda x, right? Log the likelihood of this will be what? The product of all I goes from 1 to 5 in this case, but I will do the generalization. I'll do maybe I'll find out the general formula and then I'll plug in all of these values, right? Here n equal to 5, right? The number of samples is equal to 5 in this case. I'll do it for general case. The product of all these PMFs. So it will be lambda into e to the power minus lambda xi, right? Then it will become lambda to the power n e to the power minus lambda summation of I equal to 1 to n xi. So this is my likelihood. Then log likelihood will be equal to what? So I'll take a log of it. Then it will become n log of lambda minus lambda summation of I equal to 1 to n xi. So either I can differentiate it here directly, or I can take a negative log likelihood. Let us say I will take the negative log likelihood, then the signs will change, and then I will consider this function as h of theta. I will differentiate this h of theta with respect to the parameter theta, and then I'll get what? Minus n log of lambda. What is it? Okay, theta in this case is actually lambda, right? I'll differentiating this with lambda. So it is a function of lambda, right? So minus n log of lambda is log lambda, differentiation of log of lambda is 1 upon lambda. So this will become minus n by lambda plus uh,
Summation xi.
n xi, that is equal to 0, right? And then I'll get n by lambda equal to summation of I equal to 1 to n xi. From there, if I take lambda this side, so then lambda will be equal to n divided by summation of I equal to 1 to n xi, right? And that is my estimator for lambda. Now, what I said is n equal to 5, and I know each of x size, right? So lambda hat in this case will be 5 divided by what is the sum of all of this? So it will be x1 plus x2 plus x3 plus x4 plus x5. So that is equal to 3,
20.
3 plus 3,
20.
5, 5 plus 5, 10, 10 and 10, 20. So it is 5 by 20. The estimator for this lambda will be 1 by 4, 0.25. That's how the answer is here. All right. Okay, so I think we already have seen all of that. Maybe a Gaussian mixture model, I will not touch upon that. Anyway, we will not be asking the questions over that. But if you are interested, you can, because why the reason why I'm not teaching here is in MLT we do it like thoroughly. The way it is here, right? Uh, Maybe it's like little bit confusing, and because understanding wise, right, is like little bit, I will say that it's tough in this case, because without any,
GMM
yeah,
Gaussian
differential
mixture
model.
will be taken up in MLT, right? In
MLT,
future.
yes, yes. So that way, there actually there is a good context, right? Why we need that GMM, and the flow is very clear there. Here in this course, the way GMM is defined, it is not like very clear, but we already have studied GMM kind of thing previously also in Stats 2. What was that? Can you remember? What is that? It is a joint distribution between a discrete and a continuous random variable. Remember it?
Yes, yes.
So we have seen the joint distribution between two continuous random variables. We have seen the joint distribution of two discrete random variables, and the distribution of a joint and the continuous, right? That actually will be, it will resemble to your Gaussian mixture model. Fine. Okay. Maybe there are two more topics I will touch upon. Yes, Kiran, you wanted to say something?
So do we need it for exam?
GMM will not be needed. Okay, so GM, that's why I will not teach you here. But if you are interested, maybe we can discuss it at later point of time, or you can. I think that is better. It is there in the MLT, right? There it is actually properly defined, and the context also is very clear why we need that. Fine. Uh, okay, so
So
I'll
both
just
GMM and expectation maximization both are not needed, right? From exam.
no, not needed. Yes, because the way it is here, right? I don't know. People will not be able
Yeah,
to appreciate it better. When I go through lectures, I was also like,
it was
how?
too fast and
Yeah,
yeah, actually,
correct, right? So
yeah,
and what context I should teach you? That also is a
right.
problem there. Then because GMM is not like the simple concept, right? It's like, and why it is needed, why where it is used, everything has to be there. Sir has like used that. It's anyway the derivation and everything is very correct, but where to apply it and why we are learning that, right? That is not very clear there. So that's why I'm skipping it, and generally we don't ask those questions into the uh, I think you, if you have seen the previous, I think 4 to 5 terms of question papers, it is not asked anywhere.
So in MLT, will teach it? Arun sir?
What is it?
In MLT, who will teach it?
MLT, it is very clear. MLT, it is very clear because it is in the context of unsupervised learning where I think we use clustering first, and then clustering it will be. So GMM basically is used for clustering there, unsupervised learning.
In MLT, if you can see, Arun sir has the video there
Yeah,
in MLT, so
yeah. You can
he
watch that one. That is
introduced.
very nice video. Right? So you can
I've
go
just
there.
seen it just 2 3 minutes ago.
Actually, the way it is taught MLT, right? It's the way it was very clear and much better.
And for QC also.
Yes. Okay. So these are the two inequalities we have seen, I think, previously also, and these are also important in terms of our MLF is concerned, right? So again, the applications you can see for Chebyshev and Markov both into your MLT, right? So there are like good number of applications there. Okay, what is Markov inequality? It is defined for a random variable which takes positive values, right? And Chebyshev inequality, it is also a Markov inequality, but it is readjusted such that it can be used for,
Negative also.
yeah. So it can be used for any kind of random variable, right? Okay, what is it? What Markov inequality says? It says probability that x greater than some constant is less than or equal to mu by c, right? And it depends on only one parameter here, which is what, mean, right? So mu here is mean of a random variable, and c is a some constant, right? C is some constant. Is it fine? This is your Markov inequality. There is one more inequality, which is Chebyshev inequality. It depends on two parameters, and it says that probability that mod of x minus mu is greater than or equal to c is less than or equal to
Variance of x
x by
by
c square,
c square.
right? There are like different variation to that. Let's say if your c is equal to k sigma, then how this inequality will be written as? It will be written as probability that x minus mu greater than or equal to k sigma less than or equal to what will be the uh, so variance in this case will be sigma square, right? Sigma is, let's say, the standard deviation, and sigma square by k square sigma square, so that will become 1 upon k square. So in this case, the probability that mod of x minus mu greater than or equal to k sigma is less than or equal to 1 upon k square. Is that okay? It's fine. So these are all. There are few more variations to this, but these are the basic formulas. Maybe you can solve some questions on this, and have. I think we have the questions so that, yeah, can you just solve this question, and we can discuss about that question. Is it done? One, I think I can see only one answer. Okay. Two. Okay, let us see then. What is given to me as an unfair coin is flipped 30 times. The probability of getting a tail on each toss is 0.40. Use Markov inequality to find an upper bound on the probability such that the coin lands on the tail at least 20 times. Okay, what does that mean? Let's say, try to understand that. What is the probability of success here? Probability of getting a tail, right? And that is equal to 0.40. 4, right? And the coin which is there, it is flipped for how many times? So each x1 here is a Bernoulli trial with probability zero point 0.4, correct? And the how many times it is flipped? It is flipped for 30 times. So is that correct? And it is flipped independently. Use the Markov inequality to find the upper bound on the probability such that the coin lands on the tail at least 20 times. So need how does that? So it will be probability that x is how many times, or maybe I can say the y. Y is a random variable, right? So y will be what? X1 plus x2 up to x30, right? And it is it is asked me to find out what is y greater than or equal to 20, right? And that has to be less than or equal to mu by c. Then what is the mean of, or I can say mu, or instead of that mu I'll write expectation of y, right? Expectation of y by c, and c is here is 20.
Y will be a binomial, right?
Y will be a binomial distribution, right? So in that case, what will be the expectation of this binomial random variable?
NP.
N
NP.
into P.
So n
30
is
into the
30 and p is zero point 0.4 divided by 20. So you'll get that answer as, what is it?
12 by 20.
0.6, right? So the upper bound is zero point 0.6. Suppose it was asked me to find out at least 20 times, right? If it is asked to let's say find out the probability such that the coin lands on the tail uh, greater than 20 times or more than 20 times. In that case, will that be the probability same or will that be different?
It will change, right? It will be greater than equal to 21 in that
Yeah.
case.
So in that case, it will be provided that y is greater than. So when this probability I need to calculate, right, using Markov inequality, or to find the upper bound using Markov inequality. In that case, this is exactly mean to probability of y greater than or equal to 21, and I apply the Markov inequality onto this, saying that is not equal to expectation of y will be again, then it is 30 into zero point 0.4, but your c will change as
21.
21, and that way the probability will change, right? Okay. So, okay, I think these are the broader topics which are important to your, uh, uh, for your exam, and I think these are the questions which are related to, I think finding out the marginal and whether these two
So
variables are. Yeah,
can you share this slide
yeah,
also?
yeah. Right now, I'll share that with you. So, just give me 2 minutes. I'll attach it to the
And
calendar as well.
also the notes, sir. Notes like
My notes.
today, like when we were doing the multivariate, all
Okay,
these things.
okay, okay. I'll share that also right now.
Yeah.
So where you share?
Currently, I'll share in this
Calendar.
calendar. Also, I'll give you the drive link also
Okay.
for today's session. So, and I'll ask the team to upload to the uh, portal as well. Fine. So I have attached it to the calendar. You can check whether it is visible. Also, the link is here in the chat box. This is for solve with us those PDF, right? So you can go through that. One more thing, what do you want is this one, right? It's PDF. Okay, I'm sharing this also with you, right? The only problem I think with that notes is it will start from page number 16, I guess. Okay, so when you just download it, right, you can just check it from. So you might think that initial pages are uh, empty, but they are not empty. They are. So check it from page number 16. Okay, page number 16 or 17. I have attached both the documents to the calendar, as well as you can take this from here from the chat. Okay, so that's it for today. Thanks guys for joining it. Any doubts will be there, right? I'll take it while we'll do the revision sessions. Okay, fine. All right. Okay. Thanks guys. Bye bye.
Thank you, sir.
Thank you so much.